Hello everyone, I am Sushil Kumar, and this is a video in response to this a very interesting problem that was posted in this video. The link is provided here. It's by Veritasium, and the video was titled "The Misconception About Electricity." This was brought to my attention by my friend Alok Govil. Both him and myself, we are electrical engineering graduates, and I teach electrical engineering at Lehigh University. So the problem states that we have a battery, a DC battery. In this case, I am taking it as 12 volt, and it's connected to a switch. And a circuit is made in which the wires extend to a hypothetically very far distance. So in this case, it's 150 million meters, which is the distance light would travel in half a second. So a round trip would potentially take 1 second for light to travel on either side. And a light bulb is connected on the opposite side of this, and the distance between these conductors is 1 meter. So the question was posed that in how much time would this light bulb light up? And again, there was no parameter specified about what kind of a light bulb it is, what's the wattage, and what's the dimensions of the wires, and so forth, except the fact that they are separated by 1 meter of distance. I guess this the problem is very interesting, and as my friend and I were discussing, we both learned something. But again, as we watched the video, we both felt intuitively the answer that was provided at the end of the video was not right, and for the long time we were we had a discussion, and we were quite convinced that it should not be the way it was presented, and that's why finally we got a chance, and I got a chance to make the circuit and do an analytical calculation, which I'm going to present today. Again, for this problem to work, we have to take these conductors as lossless, which means they don't have any resistance, and they don't have any conductance, shunt conductance between them, and then only we can go ahead and try to make sense out of this problem and take some examples of what kind of light, some different kind of light bulbs, and see when they light up. So I guess the original idea of this problem was to show that illustrate how electrical energy travels and how much time it can take to travel, and to kind of differentiate between the speed of travel of electrons in conductors versus the speed of travel of electrical energy. So in that sense, what I believe is this circuit is not necessarily the best way to showcase that example. And so I hope this will become clear as we go ahead. And I will be posting these notes for everyone to download, and I would encourage anybody to spot any errors or have any discussion to post their comments. So here is the circuit on the top as it was mentioned, and what we could do is we could convert this to a electrical circuit problem. And before I go ahead and try to explain this, the idea that was mentioned toward the end of that Veritasium video was, well, the electrical energy can quickly travel in space. Let's say it's air from the battery to the light bulb, and that distance is about 1 meter. So the time it takes to travel is few nanoseconds, and that's how much time it should take for the light bulb to light up. And it kind of makes sense because it's not specified the light bulb has to light up to its full brightness, fully rated brightness, and in that sense, it's a bit confusing. But several assertions are kind of made going along, which I think muddles the water a little bit. So we need to really be more specific and and try to get a little more of a quantitative description to really understand this problem. What we initially, my friend and I, both intuitively, we thought was, well, this, if at all, any displacement current, so any current, so for the light bulb to light up, it has to have current flowing through the filament of the bulb, either in an incandescent bulb or a LED bulb. In any case, the current must flow, so that current must be delivered by this battery somehow. And yes, surely it can be delivered through space as a displacement current, because the conductors have a distributed capacitance between them. But intuitively, it does not sound right that this current can be anything significant with this kind of wires, based on what we know from real experience. And that's what we find when we do these calculations as well. So as I go ahead and try to explain this, when I say instantaneous, basically that means of the order of few nanoseconds. So what the plots that will show the calculations here, they will show something happening immediately after the switch is closed, which is instantaneous, but that would be of the order of a few nanoseconds. So this circuit below kind of models this problem. So in that sense, this is a power supply which has a step function response, which is shown here with time. So it's 0 volt before 0 time, and as we turn the switch on, it immediately turns to 12 volts. So that's the time domain function of the power supply. To solve this problem, we'll go into the Laplace domain. So we'll use a Laplace transform of the various elements in the circuit. So the Laplace transform of a unit step function is written right here, 12 over s, where s is the complex frequency. We will have to do an inverse Laplace transform to find a transient response. That's what we are looking for here. This is not we are not looking for a steady state response. As you'll see, steady state is reached much later. And for that reason, we are not either looking for a harmonic analysis. This is not an AC voltage. So we will have to use our complex frequency variable as S here. Now, in this case, we are modeling the wires as a lossless transmission line with length on each side, length 150 million meters, which is shorted at the two ends. And by lossless, that means resistance and conductance are 0 for this transmission line. And the conductors have a distributed inductance and capacitance, which we can actually calculate fairly accurately. And here, to start off with this circuit, I'm taking the light bulb as an incandescent bulb, which can be modeled as just a resistor, in this case 1.44 ohms. Picking that value to model a 100-watt light bulb, which is rated for 100 watt for when connected to a 12-volt supply. So if you see 12 square over R, that's the power dissipated in the bulb, would be 100 if you use this resistance. And we can change this light bulb to different values later on. So to model the transmission line, I'm using some of the models that we typically teach in an undergraduate course on transmission lines. So this is a lossless transmission line. It's modeled as a series and parallel connection of inductors and capacitors, and that models their inductance and distributed inductance and capacitance here. So for example, a short length of this line, dx, has a inductance of L prime dx and a capacitance of C prime dx. And in this case, L prime and C prime, as listed here, are inductance per unit length and capacitance per unit length. And actually, they can be calculated accurately with these formulae. It's a standard formula for here. The only assumption here is that the diameter D, that's the diameter of the conductors, is much smaller than the spacing. If that's not the case, we can also use a a more accurate formula as well, which won't change things much. Instead of this log function, there is a hyperbolic cosine, inverse of hyperbolic cosine function here, but a link is provided from where you can see some of these formula. So here, this transmission line has, if I am just assuming a diameter of 1 millimeter here and a spacing of 1 meter as given, so this assumption, the diameter is the only parameter I am assuming here of my own. And once I do that, the inductance comes to about 3 microhenry per meter of this transmission line, and capacitance coming to 3.66 picofarad per meter. So as you can already see, this capacitance is very small to be, which will ultimately, what that means is that the characteristic impedance of this transmission line, which is this parameter, is going to be fairly large. And when we calculate that, comes about to be about 1 kilo ohms. To be exact here, in this case, it's 911.5 ohms. So this is the propagation constant, and from this parameter you can actually see the speed of light. So in fact, the speed at which any current or voltage waveform will travel in this transmission line is this phase velocity, which, assuming that the conductors are surrounded by air, it's exactly equal to the speed of light in vacuum or in air, which is 3 times 10 to the 8 meters per second. So now, before I begin, as I mentioned, let's go back to the last page. This model models the transfer of energy or current waveforms and voltage waveform in the longitudinal direction as indicated here fairly accurately. However, it does not model the time delay that happens for the energy to travel this 1 meter distance, which is few nanoseconds. So that's why whatever you see here will not incorporate or include those nanosecond. All those will appear instantaneous. So again, the original point of that video by Veritasium was to show that the energy can flow at speed of light, but the electrons actually move in the conductors much slowly at drift velocity, if you can take that as simplistic model of a current flow, which is correct. So the electrons flow in these wires when the current is flowing at very, very slow speed, but the energy can flow much faster. Now, when we say energy, that actually also means current and voltage waveforms. So if voltage suddenly rises at this point, this waveform can travel at the speed of light. And this voltage at this point between the two conductors can also rise after a split second for even such a long transmission line. And similarly, the current that was 0 initially here in the conductor, and suddenly as the voltage waveform comes, the current rises at this point, and the current waveform also can rise or increase in a split second, even for such a long conductor. In that sense, what that means is that electrons will start moving here in the conductor, and within a split second, they can also start moving at the end of the transmission line. And I think that's a good thing to illustrate, and I believe that's what the video wanted to show. And I believe this is not the right circuit to show that problem, as you will see later. So let's go back to our model. This is our model, and these are the parameters that we are using. And one of the more important parameters here is this characteristic impedance of the transmission line. So let's keep that in mind. It's about 911.5 ohms. Now, some other theory of transmission lines. So if a transmission line is terminated by some load impedance Z sub L, and on the other side, the input impedance of between these 2 points is given by this formula. And this is not necessarily a steady state impedance. The gamma, if you remember, is the propagation constant. It's going back 2 pages or 1 page here. Gamma has this complex frequency parameter. So if you leave it in S terms and you leave the S variable here, and this is it can appear in a transfer function, and it can model the transient response exactly if you take the inverse Laplace transform of this circuit when you finally solve it. So it's not only valid for a steady state. So this is an input impedance of the transmission line at all times. This formula is valid for modeling all the times in the circuit. And for a short-circuited line, Z sub L is 0. So at the ends, it's short-circuited, like in the given problem. So these go out, and then you have this simpler expression. So the input impedance is Z0 tan hyperbolic of gamma L, which comes to this value. So this length is given to be 150 million meters, and this is 300 million meters per second. So this is just S over 2. So this will be Z0 tan hyperbolic S over 2 here. That's the input impedance of each of those transmission lines at the 2 ends. In general, this transmission line could appear like if it was a AC frequency, if it's an AC power supply, harmonic power supply driving the circuit, and if you were looking at steady state, this transmission line could appear as inductive or capacitive depending on what phase you see for this impedance. But we are not talking about steady state response here, so the frequency does not make sense when we are discussing this circuit. So we're looking at transient response for a step function input. So let's do that here. And then I'll also try to, and definitely this circuit is something that I learned something more about transmission lines, and which is very interesting. So we'll see what that is. So this is the final circuit that we want to solve. This is the power supply that is applied, and this is the resistance of the bulb. And these transmission lines are modeled by the input impedance that's shown on the previous page. And so the whole circuit becomes like this. So this is a fairly simple circuit to solve. It's a voltage divider. So the voltage appearing across the bulb, which is what we are going to calculate, is V sub B. So B stands for bulb. R sub B is the resistance of the bulb. V sub P is the power supply. And the voltage at the bulb that appears is V sub B, and this is the Laplace transform. So that's the voltage at the bulb with the voltage divider relation, and this is the expression. So actually this is, I would say, an exact analytical solution for what the voltage at the bulb is, and then you can also calculate the current, which is simply VB over RB, and you can calculate the power dissipated. So to find the time domain version, you have to take the inverse Laplace transform. And I am actually using one of the very useful programs which I found on MATLAB Math Exchange for computing inverse Laplace transform numerically for any expression that's given. So that's the link will be posted there. And then we can do the inverse lap. So for the given parameters, you substitute Z0 and RB of 1.44 ohms, Z0 of 911.5, and the length of the transmission line here, and the voltage power supply. So this is the final expression for the Laplace transform of the voltage at the bulb. So you take the inverse Laplace transform of this expression, and that's how we get the answer for starting from 0 time to infinity. So let's try to understand what this circuit actually does. And for that, let's look at two different scenarios. What is the case when we have very short time? So by short time, it means the time taken for any voltage or current waveform to travel all the way to the end and come back. So this round trip time for a waveform is 1 second. As we saw, the velocity or the speed of travel is same as speed of light. So this 1 second. So before any time prior to 1 second, there is no information about this load. So in that sense, there is no reflections in that join your initial supply here. So this transmission line basically acts like a resistor, a shunt of Z0 value. And this is the pretty amazing thing about transmission lines. Despite having a distributed inductance and capacitance, they appear like a shunt, a resistor of value characteristic impedance. And again, this value here is fairly large. This is Z0, which is 911.5 ohms for the chosen parameters. This value is fairly large because this shunt capacitance is fairly small, as the conductors are quite far in air, and this actually models the circuit very well. What's going to happen for the time scale of less than 1 second. Now, for time scales of much more than 1 second, we'll come to that later. So let's first look at what happens for time scales from 0 to 1 second. So that's the situation described here for a time scale of less than 1 second. For t less than 1 second, for that time scale, we have the circuit can be changed into this much simpler circuit. In other words, that impedance Z in, instead of that, we can just replace the impedance offered by both the transmission lines as just simply a resistor of value Z0, the characteristic impedance. And in this case, this is a voltage divider. So the voltage that appears at the bulb will be this fraction of the input voltage. So if the input voltage was 12 volts, this fraction comes out to be about 0.009, so 0.01 volt. So for 0 to 1 second, so again, as I said, this is instantaneous here. So, but this will actually happen at the time scale of few nanosecond because of that travel between the two conductors of the energy of a distance of 1 meter. So think of this rise time of the order of few nanoseconds, but within that short time, this voltage across this bulb is 0.009 volts. Now this voltage is very small. This bulb is rated for 12 volts when it gives 100 watt output. So let's see what the waveform looks like when you solve it with time. So on the left hand side, this is a time versus the voltage at the bulb, and by using that we can calculate the current at the bulb and calculate the power dissipated by the bulb. So as you can see, the voltage at the start between 0 and 1 is about 0.01 volts, and then it keeps rising as the voltage waveform reflects back and comes back within 1 second and gradually rises. And this is how the circuit operates. It successively they are superimposed, the voltage rises across the bulb, and it's not easy for me to understand how why this you can kind of see that this will eventually become a smoother function with time, but that's hard to describe physically why that's happening. But this is a very slow process, and the reason this is a slow process, why this signal is rising slowly, is because there is inductance in this wire, a huge inductance in the wire. And as we'll see later, that becomes more clear as we simulate or calculate for much longer times. Now, between 0 and 1 second, this 0.01 volt is only about 60 microwatt of power dissipation out of the 100 watt. So for a 100 watt bulb, if you have a 60 microwatt being dissipated, there is some current flowing there, but it's basically you won't see the light bulb light up at all. In fact, you won't see the light bulb light up even in 10 seconds. It's 0.02 watt. So let's see what happens at a much longer time scale. At much longer time scales, all these transients slowly die out, and then the change in the voltage across the bulb is much slower with time. And so in that sense, all the distributed capacitance or the shunt capacitances between these conductors in the transmission line, since the voltages at any point in the transmission line is no longer changing very fast, the current conducting through the capacitance is proportional to the time derivative of the voltage, how fast the voltage is changing across the two ends of the capacitor. And since that voltage is no longer going to be changing very fast over time, after a period of time, the displacement current between these two conductors is negligible. And so then we can model these whole transmission line as a one large inductor. And that's also comes out from these expressions too. If you try to analyze it and you look at very short, small frequencies in your time response, it becomes like an inductor. This Z in is essentially a large inductor. So we can actually then model for these large time scales this circuit. So for these large time scales, much larger than 1 second, which is the time it takes for the waveform to reflect back at the ends, this circuit can be modeled as a lump circuit again. So either for less than 1 second or much larger than 1 second, both cases we can model this circuit with lump circuit parameters or as a lump circuit. In this case, this total inductance comes to be if you multiply the inductance per unit length with the length of the wires, this is about 455 henries. So very large inductor. So if you see this circuit, this looks like, if you look at its transfer function, it's actually you have to charge up this huge inductor, store magnetic energy, and it takes time. And the kind of time it takes is L over R in the circuit. So the total inductance is 2 times L prime L. So this whole inductance over R, this is the time constant of this kind of a circuit. It's a low pass filter for those who have analyzed these kind of circuits in terms of their frequency response. And this is the time constant. So actually, that's the transfer function for this circuit. And this time constant, if you evaluate, is about 630 seconds for the resistance that we took and the inductance. And so let's simulate, let's continue solving this circuit for much longer time scales. And exactly that's what we see. So this initial power dissipation here in the bulb was about 62 microwatt. And it gradually rises, and as you can see, it rises to eventually to 100 watt because it's a 100 watt bulb. Entire 12 volt right here appears across the bulb, but that's after a much longer time. In about 630 seconds, about 67% of the total voltage appears across the bulb. That's what the time this expression shows. And about in that case, about 60-70 watt of power is being dissipated. So to realistically see the bulb lighting up, I would say that for a 100 watt bulb, well, if around maybe 10 watt or 5 watt, you can probably start seeing some light coming out of the bulb. And that would be about few tenths of seconds at all. Well, actually, sorry, about 100 seconds for this case. For the light bulb we chose. Let's pick another light bulb, and let's say if the light bulb you chose was one from the store, which is a 100 watt incandescent bulb rated for our 120 volt main supply. And if you see that that bulb will have a resistance of about 144 ohms, not 1.44, because if you calculate the power dissipation for 120 volt supply and 144 ohms, this is about 100 watt. So that's let's put that resistor in there. But since this is a resistor rated for 120 volt supply, when you put this resistor in our circuit right here, and we have a 12 volt supply here, well, 12 volt can only supply about 1 watt of power. So if you calculate 12 volt square by 144, this is about 1 watt. So that won't be a good bulb to pick to put in front of a 12 volt supply anyway to get any kind of light output. But let's just look at this bulb, what this will give us. And as you can see, because it's got a larger resistance, the time constant L over R, the time constant is L over RB, is much smaller. So the power dissipated at the bulb rises much faster, not at 600 second time scale, but much faster, few tenths of second. But as you can see, this bulb is not the right bulb, because eventually it will saturate at 1 watt, which is the maximum wattage you can dissipate. So when you connected this bulb, it will eventually be 1 watt, and again, this 1 watt is hardly any power dissipation for a bulb to even see it being lighted. And obviously, you might start to see some light output after a few tenths of second when it reaches this value. The final case would be an LED bulb. So I just kind of took an example of what typical LEDs would be. Let's say you make a 100 watt equivalent incandescent bulb. So typically such LED bulbs consume 10 watt of electrical power, around that. So let's, I'm just taking some numbers, typical numbers. Let's say this LED bulb was made up of 6 such LEDs, consuming total power of 9.6 watt for it, and rated for a 12 volt DC power supply. And then you can look at this circuit. Each LED consumes consumes about 400 milliamps of current, and drops about 4 volts at that current rating, and consumes about 1.6 watt of power. So each LED is 1.6 watt of electrical consumption, totaling 9.6 watt for this LED, which might give you a 100 watt equivalent incandescent bulb. So if you look at its equivalent circuit, we can actually put this circuit, which is kind of a stepwise model for these diodes, into our original circuit. So that does not change our, let's go back to our original circuit. So we'll put this LED right here. So instead of this RB, now we are going to put that 1.875 ohms and a voltage drop of 10.5 volts, which is the model that I have for that LED. So one interesting thing that will happen is that the LEDs do not conduct any current unless, well, they appear as open almost, so they have a very high impedance, unless the voltage across the diodes is in excess of the turn-on voltage. So in that sense, this, when you put the LED bulb here, this will appear as an open circuit in the beginning. And since this, for times less than 1 second, since this transmission line acts like a resistor of value Z naught, this entire 12 volts will appear across the LED. However, as the current starts to flow, this transmission line, these capacitors cannot supply the current immediately. So the way it works is this voltage will the current will only again rise very slowly in this LED circuit. So this entire voltage will, the amount of voltage that will appear across this LED will be just enough to turn them on, but not have enough current flowing through the circuit. So instantaneously, which means in few nanoseconds time, the LED will turn on, in the sense the current will start to flow, but that current will again be very small because this transmission line, the large current cannot instantaneously flow through the conductors across the air. So, and that's the solution for this LED. I guess for in about 1 second, much less than 0.1 watt is dissipated. So you won't see any lighting up of the LED at all. So this is for the short period from 0 to 50 seconds, and then from much longer. So to reach its rated value or anything close to that, let's say 50% of that rated, about 9.6, it still takes 300, 400 seconds. But to be able to see some light output from the LEDs, I would say for a 9.6 watt LED, maybe even half a watt of dissipation over this whole LED, half a watt would be somewhere here, you would start to see light output. So within 20 to 30 seconds with that LED bulb, you can start to see some light output. So again, the takeaway from this is within few seconds, no matter what kind of light bulb you put, whether it's Christmas lights or incandescent or LED lights, there just won't be enough current delivered to the bulb in this kind of a circuit to see any kind of light output. Now, coming finally back to the original intention of the video, I think, if I understand right, was to show how electrical signals propagate. And I think this will be a good circuit to do that. Obviously, you just put a long transmission line, just like was suggested, and you turn on the switch here or close the switch for the current to, and then you measure the voltage across a resistor. And now this could be potentially some sort of a light bulb, as long as you make this resistor kind of match to the characteristic impedance, so that most of the electrical energy is delivered to this load. If it's not matched to this impedance, a lot of it is reflected back, and so you won't see that whatever you want to see, what kind of for example, light output you want to see on this end. So to be able to see that, that power must be delivered here, so you need to do some matching to the Z naught of this transmission line. So this would be a good circuit. So what happens in this case, as soon as you turn the switch on, the electrons, as I said here, would start to flow very slowly. So an electron that enters the wire at this end will probably will not reach here at any good time at all. But what does happen, the waveforms, or the current and voltage waveform, they do travel very fast. And within, if this was, let's say, half a second or 150 million meters, within half a second, that voltage waveform and also current waveform will reach here. In other words, the electrons, after this switch is closed, within half a second, you will see electron movement in this resistor right here. So that's the essence of, we don't have to even study or even discuss electrical and magnetic fields and that's how traditional electrical engineering is being taught. When we talk only in terms of voltages and currents, we do not, when we study circuit theory, we do not really invoke electrical and magnetic fields that much. And I think that's fine. That's you have to, it's a good idea to combine them later and to know that what's the electric field between these two conductors and what's the magnetic energy, magnetic field around the conductors when the current is flowing, and so forth. But we can stay in the domain of electrical current and voltage and still still suggest that the energy is flowing at the speed of light. And what is flowing at the speed of light is this waveform. I would like to say, I won't say current is flowing at the speed of light, because that might mean the electrons are moving at the speed of light. But this voltage, this current change, the electrons were at rest here, and after half a second they will start moving. And that does mean that the energy flows at the speed of light. So I hope you like it. I'll upload this, and I'll provide a link for this file, and you can post any comments or criticisms in the comment section. Thank you.